Okay, I think we'll start. Is it okay, Niels?
Yes, let's do that.
Yes,
So.
well, on behalf of DS Name and Maskinmesterens Forening, I should like very much to bid you all welcome to this meeting concerning digital cases in the engine room. My name is Peter Black. I am a member of the planning group at the Danish Society for Naval Architecture and Marine Engineering, or DS Name. And I'm also projektchef at the Danish Engineering Association, Maskinmesterens Forening. If I could ask you to please turn off your microphones if you are not making a presentation or speaking. We are recording the session, so if this is not desired, then you should probably log off. Digital cases in the engine room can be found both on board and on shore. It's competitive out there. Profitability and customer satisfaction are always on the line. And to stay ahead of the game, the equipment needs to execute flawlessly. Combining the latest technologies with equipment availability, safety, and efficiency is key. Today, it is less about engines and more about digitalization, and automation, upon which Man Energy Solutions and Navigator, they will share their thoughts today. I give the word now to Associate Professor Niels Tingleff Hostrup from Fredericia Maskinmesterskolen, who together with Philip Holtz from MAN Energy Solutions has organized today's meeting. The word is yours, Niels.
Thank you, Peter, and welcome to today's session, where we will have three interesting presentations from Henrik Stribold and Jesper Mark Pedersen from Man Energy Solutions and from Søren Winther Hansen from the Navigator. We will start with the two presentations from MAN, and you're welcome to type questions if they come to mind with you in the chat function along the way, but we'll keep a question session, Q&A session at the end of the two presentations from Henrik and Jesper from MAN. And then we'll have another Q&A session after Søren's presentations from the Navigator, and then we'll round up everything in the end with a short discussion and questions if there's still probably some unanswered questions, and try to close this webinar by 1800 at the end. So, Henrik, you're the first one to give a presentation.
Yes. Hello, let me just upload and I'll get started. Let me know if you can see.
We can.
Is it okay?
Yes, at least
yes.
From my perspective.
Okay.
Yes, very good.
Thanks a lot, and welcome to all participants today. From MAN's side, we're extremely happy that we received this invitation to contribute to this community with insights into what MAN is working on, and hopefully it will serve as an inspiration for others and maybe even lead to some concrete actions. Today, my name is Henrik Stribold. I'm a Senior Business Development Manager. And together with me today, there is Jesper Mark Pedersen, Head of Cylinder Condition Group in MAN. Jesper will pitch in halfway through this slideshow, and I'm pretty sure Jesper is much better at explaining who he is and what he's doing, so I'll leave it up to him. Just before I get started, I have more than 30 years of experience working with MAN, 20 years within the engineering department, and more than 13 years in after-sales business, where of the last 4 to 5 years I've been working on digitalization topics. And currently I'm responsible for the business development of the digital product that we're talking about today, and others other related products. The current or the topic of today is named Cylinder Condition Evaluation. It's a service within the PrimeServe Assist service portfolio, and all of that is powered by the MAN Xeon platform. That we will try to take you through. The agenda, a little bit about the company and why we are working on digital services, perspective into you can say the overall of the digital services, and then we'll talk specifically about what cylinder condition evaluation is all about. A little bit about MAN for those who don't know us. We've been in the game of providing technology to the industry for more than 250 years. We're headquartered in Augsburg, Germany, and roughly 14,000 people are hired across 120 sites globally. Our products are divided into three main business areas, where we have the engines and the marine systems as the one where Jesper and I are representing here. Then we have the power plant business, and then the turbo machinery business, which delivers equipment for the process industry. On the bottom part, we see the just get this. To support all these three business units, we have the after sales brand, which is called MAN PrimeServe, which is the supporting part for all the activities with the equipment that these three business units put into the market. Now, if we look at our company strategy, two of the 4 or 5 pillars we are building our company strategy on is these decarbonization and digitalization. These are, you can say, the new to the strategy part over the last 5 years. Decarbonization, of course, calls for new technology, meaning more complex engines, which require, say, more skills to operate them typically. But this new technology will also provide some opportunities to utilize new types of fuels and so on. And the last part, the digitalization, which is the interesting part in terms of this is where new business models are surfacing all over the industry. So this is what we are going to talk about today. A little map, a lot of stuff is going on here, but we are trying here to explain what is going on in the maintenance journey that a typical ship owner or plant operator will experience in the lifetime of running some equipment. And it goes like this. There is a kind of a problem or an issue with the equipment on board a vessel, for instance. There's a problem with the engine. Somebody detects that there is such a problem occurring. Then you need to issue some kind of a notification to get to some people to actually figure out what the problem is. And then start an investigation into how should we actually solve that problem, and then advise some kind of action. And then in step 5, our customer is able to prepare what kind of overhaul should happen on board the vessel, and then in the end make a report and a sign off when the problem has been fixed. The service that we are talking about, the MAN PrimeServe Assist service, covers everything from an issue is detected until we have advised the customer with an action. And during the course of this, what we are trying to do is we are trying to make it these 3 circles integrate more seamlessly than we know the cases today in the current scenario. So in every of these steps we could find along the way, we're going to provide services that will make the day and life easier for our customers. The Prime Services service solution consists of 3 elements. We have the data infrastructure, which is the MAN Xeon platform and subsequent user interface. Then we have some analytical tools that run on this in this cloud, which means that some algorithms and machine learning. And last but not least, the human expertise, because it's not about big data. It's about the combination of big data and human expertise. So here, what we do is we throw in the many years of experience we have with MAN, with developing the products and then subsequently servicing them. And this we do now on a 24/7 basis. So the customers who actually sign up for this service, they will get monitored 24/7. So these 3 elements, the platform, the analytics, and the human expertise, they make up the Prime Assist service portfolio. There's a quick link here where you can find more information about that. Up in this corner, just a brief, say, an architectural overview, nothing much showing other than we are connecting the vessels via satellite to the cloud from where the data is accessible by MAN and by the customer and so forth. Now, this service portfolio has 3 different focus areas. And the first focus area and the main focus area, as we could call it, is the availability focus. That is the day-to-day optimization of equipment health. And this part here relies 100% on sensor data. That means sensors sitting on the engine in the vessel and then transmitted to the cloud. The service will deliver a monitoring and evaluation and subsequently an advice on how to run the equipment and also how to judge the condition. For instance, the engine balance and if the settings are done correctly. Now, the second focus area is on efficiency. This is a long-term optimization here of power, emissions, consumptions, you name it. And again, driven by sensor data. And we can say here it's the in-depth over time trending across systems, across fleets, and so on. And then the last part, and the one that we are here to explain about today, that is the maintenance focus area. And that is the long-term maintenance strategy optimization. And what we're working with here is predominantly non-sensor data. That means data coming from observations or lab data and so forth. And we will also combine it with sensor data. What we are focusing on is wear rates and fluids composition. That means that we are able to judge a component condition by evaluating wear rates and fluids composition, and ultimately be able to estimate a remaining lifetime of a specific component. And yeah, so trying to speak a little bit about our goal, we can say, okay, solving customer problems. Right now, we see a lot of environmental regulations are pushing the industry for changes now. We see the shift from heavy fuel oil to very low sulfur fuels. And we also see that in combination with the new breed of high-performing and very efficient engine designs. They really require much closer monitoring and much more technical knowledge to avoid unintended wear. And this wear often can result in unplanned maintenance. And it figures that the larger size of the engine, the larger the problem will be, especially in terms of money. So what we at MAN are doing is we are trying to create this very proactive service that will help customers and operators reduce unplanned maintenance, and especially to make them keep their vessels available for the market. We know that on board the vessel there is a tendency towards the lacking of knowledge on how to operate the engine. And again, as I explained, there could be damage to engines, unscheduled maintenance, high maintenance cost, and so on. It all calls for a solution. And in this case here, the cylinder condition evaluation is our take at it. And our goal is simply to provide a service that can solve these very complex maintenance problems by leveraging the knowledge from our engineers. And my final slide here is to say, okay, then how will this service then actually work? And if we start up here in the upper right-hand corner, we have a customer who has signed up for this service. This customer will be alerted to take oil samples, some wear measurements, or other types of observations. When those, when that kind of data is sampled and acquired, it will be uploaded into the CN platform by the customer. And not only will it just be hand typed into the database or cloud, we can also upload complete lab reports and so on. Once it's in the platform, the algorithm together with the experts will have a look at it and then provide the customer with a status on, okay, how did that drain oil actually perform, or lube oil actually perform? And we will provide an advice with a meaningful insight into the problem. And the service does not stop here, because we can advise a whole lot to the customer, but if it's not understood clearly and it's not followed up by the crew, then it's practically useless for the ship owner in the end. So for that part of it, we will follow up with looking at the sensor data to see actually whether things have been followed. Yes, and now I think I will hand over to Jesper for the more detailed part of this presentation.
Yep. I will take over the screen. Here we go. Hope you're all seeing a different slide deck now.
It's looking good.
Yes, Jesper, thank you.
Good, perfect. Then I will continue from here. Yes, and thank you. As mentioned, my name is Jesper Mark Petersen. I am head of the cylinder condition group in the operation department in Copenhagen. That means we are in the operation department taking care of warranty on our newer engines, extended warranties of the still pretty new engines. And we do, let's say, the R&D testing of new components, and we evaluate, let's say, cylinder oil performance, in general, the issues that we have at hand that need to be addressed for our future engines. So we are in the daily business in touch with whatever issues come up. And for this, we of course advise internally both instruction book departments, tooling, and other aspects that needs to be addressed. There is a lot of know-how involved in doing this. I've been dealing with it for 18 years, just with the cylinder condition, and we are still learning. We are still discovering new things, but there is definitely a lot of things that could be put into let's say into advices or into more intelligent aspects, and that's kind of the vision of doing this. I can mention one issue that we had with the that's with the upgrades of the engines, the introduction of co-corrosion that led to quite a lot of severe wear down situations on a lot of engines, and a lot of those could have been avoided if only the knowledge had been present on these ships. But we had a lot of operators that unfortunately had to learn it the hard way, you could say, by having a wear down situation, and then from there gaining the knowledge of this new aspect of the engines. So it's you could say with a new generation of engines, new aspects could emerge, and how do you successfully put that kind of knowledge on board the ships? That is actually a huge task. There is let's say a very slow movement of knowledge from my side, where we see it the first, until it actually reaches both our own prime serve hubs, but then again, before you can imagine that it's taught into the engine crews out there, and then how can we improve that aspect? So we have a vision. The vision is that a lot of this knowledge data that we collect, we, for the two-stroke engine advice, also for four-strokes, a lot of inspection is done in port, that is gas port inspections, sparing inspections. There is always a lot to do to maintain the engine, and a lot of these aspects are usually dealt with the crew experience or the crew knowledge, with some guidelines from our side. So that's one aspect that is not addressed in the digital solutions yet. But this is what we want to combine into this feature with this cylinder condition evaluation in the maintenance. So how do you do this? We have, as I said, a lot of instruction from our side. You've probably seen our instruction books and all the tables for monitoring. And in addition to this, there is a lot of other features which are usually taken care of by, let's say, oil companies, giving instructions on this chemical composition of the lube oils, and how do you couple these things together? That's the big trick that we want to assist the operators in doing. I have some mock-ups here from the screens in a way that we could expect it to look. It's just mock-ups, so the intention is to be able to give transparency of the general health of the engines in the different aspects that there is. For a given vessel, there will be, you could say, issues related to the engine sets they have on the ship. Could be the auxiliary engines, could be the main engine, and in those aspects, there could be connectivity aspects. There could be a drain oil aspect, there could be a maintenance aspect or a performance aspect, and these could put into categories to give an easy overview for the operators to be able to get this fast and efficient transparency of how the fleet is doing. So having in this broad overview, which is of course relying on the algorithms that we have in the background to look at the evaluation of the data that is on one part given by the sensors and the other part coming from the crew itself when they're reporting the observations they have. That aspect will then assist, of course, for the superintendents, fleet managers ashore, but it will also have a possibility of going more in depth, looking at the SDA for the given engine, or it could be looking at running hours for the individual cylinders on the main engine, looking at overall history to see how is that single unit actually doing. And as Henrik was mentioning, our let's say far-fetched goal is to actually get into a possibility of calculating estimated remaining service life of the different components, and also with a let's say, a hope that we will be able to justify, let's say, recalculations. So meaning that if you change parameters for a given cylinder, increasing lubrication, reducing Pmax pressure, then giving an offset of the expected lifetime to be able to postpone a given overhaul in case you need to actually push the ship further. So having instead of a fixed overhaul period, having a more flexible overhaul but realistic, looking at the present situation, looking at the history of event for the unit, so the wear history, and then looking at the data coming in at the moment, engine performance, drain oil amount, and estimating forward. So a small crystal ball for every cylinder, for every component. That's the goal of putting such a maintenance scheme in plan here, because we want to go onto a more condition-based kind of maintenance scheme than what we have. An example here could be drain oil, which is I wouldn't say overseen, but it's something that we use. We give minor guidance on drain oil values. We don't give a complete overview of the different threshold values and the dependency of the different aspects. We have a lot of in-house knowledge. We have been using drain oil analysis for the past 20 years for our R&D purposes, and we also use it quite a lot for our warranty troubleshooting. So this is something that we have a lot of in-house technology to assess. And the trick here is to bring it into a template where it will be feasible for the engine crew, so that they can enter a simple set of data, as you see here, and then based upon the entry that they have made, be able to give them a timely alert, giving them some instructions on what to do next, how to prevent this from accelerating beyond the control of what they have. Again, we have had numerous cases with the co-corrosion where crew have been alerted by drain oil analysis coming from the oil companies. They were clear indications that the engine was going astray and that the wear down would be out of control, but still they do not react until they have broken piston rings, and by then an accelerated wear of liners of 1 to 2 millimeters or more, and then ending up with a loss of lifetime, which is more than halving the lifetime of the components, and of course not to anybody's satisfaction, of course. And this we want to go more proactive and prevent from happening in the future. And we can do that by obtaining the service observation from the crew and then linking it to our own guidelines and our own knowledge database. This would then rest on, of course, a number of cases. So at the moment we are trying to mind pick all our experts and put it into paper. What should be the thresholds? What is the conditions? What are the connections between copper, chrome, iron values? How do you link this to running hours and etc.? So getting all this knowledge put in place, there could be repeats of certain events that we need to put in there. And once we have all the basics in, this is what we will do firstly. Then we will work into a machine learning, and where we can collect the data coming from the ships. And by that, we will be able to put even better advice, again, based on our knowledge of how these things actually correspond to each other. We will be able to put that into a more intelligent way of looking at the engine performance and the engine components lifetime. It would be possible to advise on replacement of fuel valves prematurely, because we could see an influence, for example, on the cylinder condition, and this would mean that you could perhaps give even more running hours on your piston rings because you don't subdue them to a faulty fuel valve, for example. So that kind of knowledge we would be able to put into the system to prevent these cases from happening. And that would be a benefit from our side to be able to take these cases based on this logic that we put in there, and then put that into advice to the engine crew. If we're in I think there's a target here, both from PrimeServe for a service, but also from our point of view, from warranty. There's a big advantage in having the best performance of the engines. At the moment, we have, as Henrik explained, a scheme of connecting the vessels. That means collecting sensor data from the engine, bringing it into the cloud, and from there into the RSC, where we can give advice and we can follow the engine trends. We can run some basic trends. So we can do some algorithms also at the moment where we can see. We can alert when certain things are happening on the engine. It's not proactive at the moment. We can see the condition and we can give advice based on that. And that is, I think, what a lot of the focus has been to look at the engine performance, look at the sensors, and put that in there. What we want to do is to couple this to the inspection data that we have from the crew. The only way to get a complete photo or complete overview of the engine condition is to have sensor data and the inspection data that we have. It's not easy, as the sensor data is time linked. So this runs fluently based on, you would say, a clock hour, whereas the manual data that we are receiving usually from our superintendents or from the engine crew is usually in relation to the main engine running hours. So it's a timestamp. You have your sensor data which are running fluently, continuously to you, but then you have these pictures and momentary pictures from the port stage where you can see some snapshots of the condition, and you need to link these things together to be able to predict what's actually happening. So you have to be able to see the last state and condition of the engine, and then try to decipher the sensor data from that. So linking these two things together is it sounds probably pretty easy, but in reality it's not that simple at all to be able to have a prehistoric, let's say, event, and then link that to the present situation coming from the engine. One, I would say, assistance in doing that is doing what we call the drain oil analysis. As I said, this has not been part of our instruction book so far. It's something that we are guiding against, especially when you're running with high sulfur fuels. But taking a sample of drain oil, and to try and explain a little bit more on that, so the drain oil is the leftover cylinder oil once it has been utilized. So we have two lubrication systems on the engine, one being the system oil, which is used for bearing lubrication, piston cooling, etc. And then we have the cylinder oil, which is a one flow system. You don't reuse it. It's injected for lubrication, but also for a lot for neutralization and for detergency purposes into the piston rings. And from there, it's utilized to keep all the components free moving, but also to react, as I said, to neutralize. Taking these, the drain oil, so the used oil from there, and having it analyzed for salts and iron values, this gives us a good knowledge of how the engine is actually running, how the tribology is working. It also gives us an insight into other aspects. So we can see if there are, for example, seawater coming in, if there are some aspects there coming, if there's system oil causing dilution. There is a lot of aspects. There's vanadium. There's a lot of things that we can read from this sample, and similar to taking a blood sample from a human, where you can also see a lot of different values, and linking them correctly together, you can diagnose people with different diseases. There's a similar pattern when we look at drain oils, and you can look at the aspects of iron. You can see what type of iron we're talking about. Is it magnetic? Is it non-magnetic? And we can look at other tracers to see what might be the cause for an excessive magnetic iron, what could be the cause of this non-magnetic iron, and this would give us an insight to be able to actually predict what's going on, but also where would this end. So again, lifetime of the components could be based on this, but it cannot stand alone. As mentioned, you need to have also the inspection insights from the crew, and this is the trick, to be able to collect the manual observations, initially collecting the measurements that can be done, trying to specify as much as possible as a measurement that can be performed by the crew when they do the inspection, coating thicknesses, clearances, collecting all of this to be able to get this overview of the engine state. And on a future aspect, how do we couple photo material, for example? So we are looking at that also. We want to be able to, there's a lot to learn from the visual impression of a piston ring. It may not be something that you can see from the measurement of coating. You cannot see it from the drain oil, but by looking at the surfaces, looking at fatigues and cracks and burn marks, looking at deposit building up on the ring lines, this is clues that we need for the puzzle. And this is what we will be building in the future, to be able to collect more clues and putting all of this together. That will bring us to a place where we can actually give a lot of good advice. Last slide I have is to say that there is always a concern of reliability of data. Sensor data is very trustworthy because it is where you could say you have calibrated sensors. It's giving a reliable feedback. Whenever you link in a person to collect a measurement, you always run the risk that this person is perhaps misinterpreting, misreading, or simply not capable of taking a simple measurement, and that could end up with some kind of misconclusion to what actually is the engine state. So this is also something that's part of our package and our aspect. We want to build it. Firstly, we need to put the logic into our computer system so that we can deal with it and we can conclude from it. And second step, we need to secure the data flow, and this is something that we are working on a mobile platform, saying that if we can have the inspection done inside the engine on a mobile app, then you can also secure that the data seems correctly, and you can confront the person inspecting real time, asking him whether he is actually seemingly believes this is correct, whether the measurement is correct, because we can do a validation check, not after the inspection, but during the inspection. And so this is also part of the scheme. So getting valid information into the system that can then be deciphered by the system. That's part of the loop to be able to bring the service in there. So to get something just as reliable, hopefully, as the sensor data is. And that we will solve by a mobile app approach to collecting the data. Once all this is together, I think we will have a very valuable package for any operator, where you can get valid data from the crew, deciphered and interpreted by our in-house knowledge, and then brought back to the ship superintendent and the ship crew in the ways of, let's say, easy, transparent overviews, but also with monthly reports and scopes like that, to be able to give you a clear and easy readout of what is the present state and what is the maintenance planning that you need to do. Yeah, that was a short insight from me.
Thank you very much, Henrik and Jesper. We have a few minutes before the next presentation, so I would like to invite questions. If anybody has some questions for Henrik or Jesper before we continue. There are no questions in the chat as far as I can see, so everybody, you're welcome to come with your questions if you have any. Appears not to be the case, but then perhaps you can elaborate for my sake. If I understand you correct, Henrik and Jesper, is it correct that one of the ideas with this is that you in your remote center keep track of all the data so that you actually alert the ship's crew of issues they haven't seen themselves yet? So if I was a chief engineer on a vessel, you would bring to my attention issues with the engine that I might not have foreseen myself.
Yeah, I can say that on an overall level, what we are not trying to do is to mimic the systems that are already on board the vessel. That means alarm systems and so on. There are already such stuff on board the vessel. So that is not what we are trying to do. But what we are trying to do is we are trying to anticipate and be proactive. So if we can catch something before it turns into something real bad, that is where you can say we try to frame it.
Yeah, you would say we will try to automate a lot of the knowledge that our service engineers have, so that you get an immediate response, which are in scope of what you would normally have if you reached out and touched a person and talked to the superintendent. You get this automated, and of course, if it's beyond the normal cases that we see, it would give you an advice to contact the ROC, or the ROC would actually get in touch with the crew and say, well, you have a special case. We've been looking at your data. Please elaborate on these. We need this and this data to be able to go further into this case. But the idea is to, first of all, to get all the basic knowledge, the basic know-how listed, so that we can give a fast response to the normal cases. But also, by having it as an online platform, it would mean that if we discover a connection between copper, chrome, and iron that is new knowledge to us, we will be able to put it into the algorithms, and immediately you would have it transparently on all the ships which are connected. And again, if you have to wait for a traditional approach where we put out a certain paper, it gets published, it gets into some kind of school books, and then 20 years later, it's common knowledge in the fleet. So that's definitely a very slow pace to get that into the engine crew. But putting it into a system where it immediately becomes publicated to all the engines, to all the crew, would make it possible to actually catch a lot of these, as I said, where you have to learn it by doing. And there's been a lot of cases with a lot of operators where they had at least one ship which needs to fail before they discover that there's a new aspect with the new engines. And that's kind of it's a pretty costly way of learning new technology if you have to fail first. But we would be able to push that straight to the ship crew by having it in this kind of algorithms.
Sounds interesting. Yeah, a well-tested but a very expensive way of learning.
Yes. But yes, it's the old school way to do it.
It's the old school way to do it. But for instance, your example with the drain oil samples, is that correct? That the samples themselves are still the ship's crew that needs to take the samples and analyze them. So that process is not yet automated. Is that correct?
No. We have a constant awareness to see if we can automate things with sensors as much as we can. So we have been looking at BN sensors. We are looking at iron sensors online, which will collect the data without crew interference. But there are so many limitations to sensor data. Similar to measuring clearances, you cannot do that by sensor data. You need, or you can, but it's too expensive. So we could put a lab on a ship, as some called it, where you could do this analysis on board, but the expense is just too huge for any operator to put that in there. So we've tested and tried it. Some operators have opted for some ships to do it, and then usually it ends up with being too much of a cost burden. And then we fall back to the more simple, cheap ways of looking at it. So yes, there will be some crew dependency here where they have to draw a sample. And that's also why second step would be to go, let's say for the measurement at least, to go into this mobile app platform, because crew they have variation in performance. Some are very keen and very dedicated to measuring wear on the engine. Others, they have no clue. Some even falsify data because they don't want to go inside the engine for, I don't know, different reasons. But we hope to be able to kind of look into that and make sure that there is a thread or a red line of the data that they're collecting, and be able to give them a real-time advice saying, are you sure that your measurement is showing 0.7 because 200 hours ago you measured 0.4, and then this is quite a heavy wear if this is correct. So, but you need to do that real time when they're sitting inside the engine, because once they leave, close up the engine, box it up, and even start it, then it's then the chance next port.
Windows closed.
Yeah. So that's also part of our awareness. We need to make sure that we can data validate, and for that we need to not only put in the algorithms into the CRM platform, we need to also look into a more mobile way of collecting, and that's even that is a ball game in itself. Even our superintendents are a little bit skeptic of talks about bringing a mobile phone into an engine just to be able to collect data. But
just having connectivity could be an issue.
yeah, even that.
Yeah. Okay. Thank you, Jesper. I think for now we have to move on, and I would like to invite Søren for the next presentation, and then hopefully we can round up with some questions for Søren and in general in the end. So, but the time is running.
Thank you, Niels.
So, Søren, floor is yours.
Yes, can you see my presentation?
Yes, we can. Thank you.
Okay, so the presentation is called Intelligent Use of Data in a Ship. And it was a very interesting presentation, the two presentations from MAN. And I think I'll touch up on some of the things, especially with the connected vessel that they were mentioning. But this presentation is based on how do you optimize a vessel's operation based on the data that you log on board. So it's not only engine data, it's also data related to many aspects of the operations of the vessel. And there's a lot of stakeholders that are interested in how the vessels operate, for example, from a maintenance perspective, but also for an operational and commercial perspective, and especially with the latest development on the compliance side, there'll be a lot of compliance related subjects where operational data will go in. So an optimized vessel is a key, has been a key always, but is even more a key in the future. So it's a little bit about seeing the vessel as a whole. So my name is Søren Winther Hansen. I'm an independent consultant in working out of Svendborg. I have a performance company, and I do consultancy for the shipping industry on performance issues. And I have developed a piece of software to handle all the issues that I get from ship owners and operators. I'm a naval architect and a master mariner. So I sailed for many years, unfortunately for you engineers, in the wrong end of the vessel. But I sailed there for around 15, 20 years, and then I went ashore, and then I started to become a naval architect. And then I got a PhD from DTU. And I've been working with performance and data. I started with AP Møller Mærsk, and I've been around different companies, setting up systems, doing performance analysis for different companies. So operational data. So now we heard about all the sensors that are placed in a vessel, and we have gone from manual reporting to automated reporting. And of course, there's still, as we also heard before, there's still a use for the manual report. There's still the use for the eyes on board the vessel. But since we are getting a lot of data, since we are getting connected. Now that's an example from the first EEE vessels that Maersk came out with. So it's like 20 or 100 sensors hardwired into the main control system, and 200 just on temperature and measurements and operations. And there's a lot of data generated in the vessel every day. And a lot of those can be used for the various purposes that the stakeholders they are interested in. So combining that with the crew on board, the crew's knowledge, and the crew's being on board and being close to the equipment, that's of high value, and that's something that should be investigated more, I think. If we're looking at the optimization side of it, of course, a ship owner, he's interested, or he or she is interested in being able to sail the next day, so being able to operate the vessel. But you can look at different ways of operating the vessel. So you can look at operating in the most efficient way, and defining on or depending on the purpose or the perspective that you have for what's the most efficient way, there can be some clashes in between, let's say, for technical performance versus operational performance. So the technical guys, they are interested in maintaining the vessel the best way, and the operational guys, they are interested in maximizing the profits. So the clash between what's the most efficient way of operating a vessel is often there, and that could be an issue. If you're sailing with very old vessels, like there's still many vessels, old vessels in the market, so you might be interested in retrofitting the vessel to operate it more efficient. So you could look at propulsion optimization, machinery optimization, and ESDs, and increase the volume and the cargo. And of course, you can go for more new vessels and more, let's say, more energy efficient vessels when you go for new builds. And then on the environmental side, there's of course complying to all the regulations. So there's the SOx cap, the sulfur cap, that's the latest one, but there's coming up a new set of regulations in 2023 where you have some engine power limitations on a lot of the old vessels, where you have to look for what does that mean when we come to operations and when we come to maintenance. And then there's all the other issues or all the other compliance and regulatory aspects that you have to take into consideration. So data can be utilized in many ways and can be utilized for operational optimization in many ways. We saw the connected vessel before. So if you look at a vessel with all the sensors that its equipment, of course, the data is collected in the vessel and it's available for the vessel's crew, and they can look at the data, and then they get alerts if there's something wrong, and this is the way they operate the vessel by interpreting the data. The data can be sent for sure, as we also saw, for example, to man, and then they can interpret the data either by getting all the data or by getting a sample of the data, or even go on board and log into the systems out on board. So I've seen many systems where you can go in and look at what they see in the engine room, what they see on the bridge. You can see the radar picture, you can see whatever from a remote installation. And you can also have all your data sent to shore. But basically, what you should aim for is to have the valuable data sent for shore, and then the rest of the data should just remain on board if they are not necessary for the analysis that you're looking for. So you have to be able to define your analysis and then define the data that you're looking for. Basically, if you're looking at maintenance and if you're looking at the state of an item or device on board or even the whole vessel, then you need some design data to define a baseline, because a baseline tells you what should I expect for this component or what should I expect for this vessel. So some design data to define the component's baseline is one thing. The other thing is then the sensor data, the operational data when you operate the component or the vessel, and then some manual reporting of what you can do with the sensor. And then sometimes you would put some third-party data into the loop also. So if you're looking at weather, for example, you can get that from a third-party provider or position data from AIS providers and so on. And all the data that you collect, you put it in what you call a data lake. And the data lake is basically the container for all the data. And some of it you would need, and some of it you just say, okay, I have the data, but I don't need them for the analysis that I want to take. So you put it up in a data warehouse, you define the analysis that you're looking for, and then you take the data that your baseline defines that you need, and then you take them up to the warehouse. And then you do the analysis module on top of your data in the data warehouse. And then you make a presentation layer. And of course, the interest here is to make a presentation layer that gives meaning to the one who is using the presentation layer. So a lot of data coming in a data feed, that's interesting, but does it give any meaning to the end user? So there's a lot of data, a lot of measurements, a lot of time series that you can look at, but does it give any meaning for you when you look at them? And by the way, are they correct because they are sensor data? So is there anything wrong with the sensor? Do the sensor need calibration? Or can you count on the data that you get from the sensor? So you need to do some sort of data validation before you start doing the data analysis. And to do that, you also want to, let's say, make a connection between the data. So you log all these data, but how are they connected to the system that you define? So if you take a system like the one that's defined in all these boxes here. So we have on the right, you have the internal system, and then on the left, you have the external system. And you get data from all the systems, and you want to combine them into something meaningful that says something about how is the vessel operating, and is it operating in the best way that it can. So you have the connection here between the internal system and the external system. This is the propeller in this case, because on the left there's all the weather and the environment and the draft of the vessel and so on, and on the right there's the engines and the shaft and so on. So the combination between internal and external system, you need to set up baselines for that. So what's the baseline? What's the impact if it's the wave is 2 meters from forward, or is it 4 meters from forward? So what's the impact on the operations of the systems inside the vessel? So you can set up those relations, and then you can set up a KPI, because we can then look at the number, and then we can see if the number is good or bad. But if we don't know much about it, then it's problematic to see if it's good or bad. So you need to set up what we call a KPI, right? So and you can highlight it in some way if it's a warning or if it's not a warning for the data output. So that defines a good system that's valuable for the end user. So there's no man in the loop. There's only sensor data. So how do you know the data that you're getting? Are they the right data that you're getting? So one thing you can do is set up sensor dependencies. So which sensors are related to other sensors? So you can do set up the sensor relation in a sensor fusion process. And you can use the sensor fusion to detect outliers and errors, for example, because you know that a couple of sensors or a set of sensors are connected in a certain way. And if one is off, then you can get a warning or an alert because it doesn't match what the other sensors are doing. Let's say if you want to calibrate or you have a torque meter and you have torque measurements on your propeller shaft, then sometimes you would need to calibrate that. Sometimes there's slow drifting on the torque meter. So how do you know that? So you need to set up some relations and do what we call a sensor fusion process. And you can also use sensor fusion to replace runners parameters. Let's say you have a sensor showing an error for a while, it's broken or it needs replacement. If you know the relation between all the other sensors, then you can have some expected values from the broken sensors until it gets fixed. So data quality is really something that you need to include in your analysis and your evaluation of the performance of the vessel. So some samples here, we have some speed sources on the left. So one is speed through water, and one is, now it's in meters per second. So it's around 25 knots. So it's a container vessel apparently. So you have a green one that's the speed through water, and the other one is the speed over ground. So there's some current here. So sometimes they are like the lower ones, and sometimes they are far from each other. And if you use the speed, like say you do the relation between speed, power, and fuel oil consumption, if you use a different speed than you really sail with your vessel, then you get an offset on the analysis value that you're getting, and then you can count on the analysis. So you have to be aware of there are some calibration issues. If you take the pictures on the right, there's one load, there are two load diagrams, one with sensor data and one with new data. So it's manual reported data. So you see the new data, they're all over the place, and the sensor data, they are more aligned to the load diagram. It's the same for the SFOC plots that you see below. That on the left it's sensor data, and on the right it's manual reported data, and you'll see that some of the SFOC values are way below that we expect than the model says it should be. And that could be reasons that they have on board to report a lower fuel oil consumption, or there can be a calibration issue with the torque meter. The left one is, you see the SFOC values are all over the place at low loads. That's probably a flow meter issue. So what you want to do is you want to take the data that you can use, and the rest that is faulty data, you just filter them out in an analysis. So we can look at this one, for example. So you can apply some filters, and you can say, well, there are outliers in all these sensor data here. How should we set up a filter that gives a reasonable result for us? And of course, you have to know which filters you apply. You can also apply some techniques, like we heard the machine learning and artificial intelligence before, and that's not something that's widely used in the shipping sector yet. It's something everybody is talking about, but when it comes to it, it's very simple analysis that's going on. But with the amount of data that we get from sensor data, it's obvious to use these techniques to do analysis, and also for fault detection and error analysis. So that's one thing to put in mind. We saw this nice presentation about cylinder, and so when I heard Man was coming, I was thinking I shouldn't take any analysis examples from the analysis that I have done, but I've taken one anyway, and then we can always look at that if it makes sense. But generally, what you want to have when you, because at the main engine, it's consuming the fuel. It's where most of the money goes. So the bunker goes to the main engine, most of the bunker. And of course, you want a well-functioning main engine. You want the optimal SFOC. You want it to run at optimum conditions. And of course, you need to know how is that? How is the flow in the main engine, the airflow, the fuel flow, the pressures, and the temperatures. And so if you're looking at the performance of a main engine, well, there's online data and there's electronic control engines, but if we're going before 2015, for example, the engines that were delivered in vessels, which there's probably 15,000 vessels sailing around with all main engines, they don't have the ability to do all these checks, electronic checks, and connect it to different fault detection systems. So you have to do it a little bit differently. So I was contacted by a guy who had a failure or they had an overhaul on the main engine. It was quite costly, and it wasn't kind of planned for them. He was an operator, and he had his vessels in technical management at an external technical management company. So he gave us a lot of data, and as he said, can you see anything on the main engine performance data? Because they do main engine performance tests every month. Still, I think in all vessels. So you go up in load on your main engine, you do all the measurements, and then you analyze the data. So we got all these data, and then we tried to do an analysis with the means that we have. So we looked at different pressures, set up some indexes. So we can set up some indexes for Pmax, the compression pressure, and the scavenging pressure. So it says something about the moving parts, the pressure in the engine, and also the airflow over the engine. So if you set up a relation between these, and then your baseline is the shop test, then you can define what's the good area here and what's the not so good area. And you can see it if we look at those indexes here, that there's a large drop at some point where these indexes went down, and then you can combine it with some other plots where you're looking at thermal load on the engine, you're looking at pressure deviations from the mean, and then you're looking at turbocharger RPM and other ME parameters. So in fact, it was easy for us to detect where this failure was. And of course, they detected on board because they had a breakdown on the engine. So with a few means and a few relations, it's possible even for the crew on board. Because if you look at one number, then it might not give you the answer that you're looking for. If you combine the number in relation with other sensor data. Now, this is not sensor data; it's manually reported data. But if you do that, then it's possible for you to see a pattern if something is on the road to failure. So that was just an example. All these vessels from before 2015, they have these engines, and of course there's something they can do to make them run more efficient, and there's some suggestions here from MAN, for example. So one of the things that we have been looking at is the diameter of the propeller and the RPM of the engine. So if you're looking at Japanese bulk carrier builders, they haven't changed the hull design since 2005 or something like that. If you look at a Kamsarmax from Oshima or something like that, it's the same hull form since 2003, for example. But they changed the engine. They changed the engine to a engine with a low RPM, and then they increased diameter on the propeller, and suddenly they gained 10% on fuel oil consumption. In fact, it's a lot. And then they did some modification in the aft and put some swirls on rudder bolts and so on. Then they got another 5%. And suddenly they complied in the design with an old They changed the bulb, by the way, also. They have no bulb anymore. But anyway, by doing small modifications, even though they are expensive at the moment, then in fact you can gain a lot. The D rating that's given here as an example, it's connected very much to the diameter of the propeller and of course the lower RPM of the engine. And we saw lubrication is one thing. For older engines, auto tuning is another thing. For low load operations, which many vessels are running low load operations. That means the design point that they were designed for, they're running very much below that. So you can do a lot on the improvement of the SFOC on a main engine if you're running, if you're interested in it. But the question is the owner or the operator interested in? Because the driver here, it's what's the benefit for the operator or the owner, and the market is driving whatever the owner or the operator does. So if it's of a benefit for him to have this done on board his vessels, then of course there's the cost of the fuel oil. But if he's chartering his vessels out all the time, then the charter pays for the fuel oil. So the owner, he's not really interested in doing much until his vessel is so outdated that he has to do something. So unless the market changes, the owner and the operator will not change anything, because there's nothing he can. Now you see the EEDI measuring point is giving in this graph here. So whatever he's suggested to do here, or almost whatever he's suggested to do, it has an improvement outside the EEDI regime. And that doesn't give him on paper any improvement. And that doesn't make his vessel more attractive in the market. So that's why he's maybe not so interested, because as long as he has charter rates, he's not interested in improving anything on the fuel oil consumption. So that's a consideration to make. There's one here. That's an example of optimal auxiliaries operations. That's for container vessels, where vessel number 2 is operating. It's generating almost the same power as vessel number 4, but there's 12% or 10% difference in the fuel oil consumption. So there's a lot to gain to look at the operational aspects and the way it's operated. And if you can benchmark similar vessels, then it's fairly easy to see where the outliers are, where they are not. My time is almost up, so I'll just jump over I'll just go a little bit on the new regulations, because one thing, when we get close to 2023, we will see some new regulations for vessels. So everybody has to comply to a certain target. If it's a pre-EEDI vessel, then you have to comply with you get issued an EEXI. So that's an EEDI for an existing vessel. And you have some CO2 emissions targets for 2030, and you have to be below those. On the EEXI, you already know now, if you calculate the EEXI for your vessels, you can get a number, and then you can actually see how much less CO2 you have to emit when you reach 2030. So if you want to operate your vessels before or after 2030, you have to comply to these numbers here. And there's different ways to do it. On the right, you can put an engine power limit in, limit the power on your main engine. You can change your fuel to something else, or do a retrofit that makes your vessel more efficient, or you can build a new vessel. You'll probably see the EPL, the engine power limit, on many vessels. So that's something that is going to be installed on many vessels in the future. So a limitation of the power. Some vessels do have to limit the power with up to 50% or 60%, and some are steam turbine vessels. I don't think they can operate in the market after 2030. So it has some implications on the main engine. And then there's something called the CIIs, and that's the operational indexes. So efficiency has a great importance in the future, because now it's part of compliance to regulations. So that's something that you need to take in consideration also in the optimization of the operations of your vessel. An outlook to the future. So as we saw from man, well, increased digital opportunities. How can you digitize more and make more things more automatic and more smart? And then sensor fusion, AI, and machine learning opportunities are obvious when you're working with large data amounts. And then, of course, in all that big data talk that you are talking about, what is it that you're looking for? So clean the data and make some meaningful analysis that people can understand, because you can drown in all the data that you see. And are you drowning in the right data or in the wrong data? So you need to know something about that. And then translate it to somebody who has the decision-making opportunity. So decision makers, they don't always understand all the technical issues. So you have to make some sort of translation so they can understand it. And then, of course, that will create transparency in the sector. So it's my hope that we can share data more than we do in the shipping sector, because the shipping sector is a very closed environment, and there's not much data sharing. Of course, that's competitive issues, but I think at least with the new environmental regulations, there'll be a lot of more data sharing in the future. And all this will probably also create increased autonomy in the future, because when you get to sensor fusion and connection and the connected vessels, we'll probably see more of that. Thank you for your attention. That was my presentation.
Thank you, Søren, for a very interesting presentation on data. Anyone in the audience may have some questions or comments here in the last minutes? Then you're very welcome. Or I'll start. Søren, all these data, do you envision that the crew of the vessel should work with all these filters on the data, or do you envision that it should be presented to the crew, the relevant data presented for the crew in a way that is designed by you or by shipyard, or how do you think that should work?
I think we should include the crews more than we do today, because a lot of these systems that are being built, it's for the land organization, and it's then the responsibility of the land organization to convey all these information to the crew, and very often it doesn't happen. And maybe if it happens, okay, it doesn't happen in a way that the crews are able to understand it. So I think that's definitely something that should be worked more on.
Yeah, because when I look at and listen to your presentation and see all the data that is or could be potentially available for operator and crew, it sounds like there needs to be some kind of digestion of the data. So if I was a crew member, I need to have it presented in a way that is meaningful. And I don't know how far away we are from having that digestion and presentation. So it's actually supporting my decisions.
Yes, that's to define a system like that. It's not straightforward, and I think you have to know you have to know the mindset also of the crews, right? So you need to have an idea of the environment that they're working in, and how is it that they think of different ways and different things. So I don't think it's straightforward, but it's possible. Definitely, it's possible.
So could that be an area that needs further research or investigation into?
Yes, I know that there are performance companies that provide performance services, and of course some of them are looking at this already.
Okay.
But I would like them to take it a notch up, so there's more information for the crew, because the crew. So when you contact the crew and you discuss performance and optimization and the right way to do things, they are very interested in what we are saying. It's just a matter of contacting them and talking to them, because you can do magic when you start talking to people about things that interest them. So and they are there 24/7. So why not?
Absolutely.
Yeah.
Interesting, and still a lot of interesting things to work with and people to talk to.
Sure.
Okay. Thank you very much, Søren. Yeah, there's a comment from Thomas who fully agrees that crew must be involved. So absolutely agree with you, Thomas. Any other questions or comments from the audience that you would like Søren or Jesper or Henrik to try to answer? Still have a few minutes left. That appears not to be the case. But in that case, I would like to convey my thanks to Henrik and Jesper and Søren for being here today and presenting interesting views on digital cases and data-driven a data-driven future for vessels. I think it has been very inspiring to listen to and be interested to pick up on how to use data in a meaningful way for the crew in the future. And from my own perspective as a lecturer, it'll be interesting to see how we can prepare the next generation of marine engineers for all of this, and how this eventually could influence the design of the marine engineers education. And I think, as you mentioned, Jesper, it's on the long run. It's not something that's done from today till tomorrow, but how we can develop even education and further training in this respect. So from my part, yeah, thanks to all of you presenters, and thanks to all of you who joined this session today and decided to listen in and pitch in. It's my pleasure to be the new chairman of this Skibsteknik Netværk, and Peter and myself and the steering committee will join tomorrow and look into our experiences so far and how we could put together an interesting program for the autumn as well, for the next sessions in the network. And hopefully we can even have at least one physical session where we can meet somewhere in the country and get together. So, any other comments from presenters, from Peter, from Bjørn?
Thank you.
No. Okay. Then thank you, everybody. And with 5 minutes to go, then You've earned 5 minutes of breath air before dinner or whatever you're up to next from today. So thank you very much, all of you, and good.